Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Symmetry is the language of patterns, revealing the hidden structures of our world, from quantum physics to the architecture of the abstract.
Welcome to This Explainer. Today, we're diving into something truly mind-bending. We are going to explore the beautiful, universal language of symmetry that silently governs the structure of our entire universe. It's this incredible mathematical framework that touches literally everything, from the plastic puzzles sitting on your desk all the way to the very fabric of reality itself. To kick things off, I want you to ask yourself, how on earth could a plastic 3D puzzle possibly share the exact same DNA as the fundamental forces of subatomic physics? I mean, it seems like a massive leap, doesn't it? How can twisting colorful little squares relate to the microscopic behavior of quantum particles?
Well, the answer to that massive leap is group theory. You can really just think of it as the foundational operating system of symmetry. It provides this incredibly rigorous algebraic framework for analyzing invariance and structural transformations. So whether you're mapping out abstract number fields or modeling the cosmos, this is the exact architecture you rely on to understand how systems can completely transform yet remain structurally sound.
So here's our roadmap for today's explainer. We're going to cover 1. The language of symmetry, 2. Subgroups and hidden structures, 3. The atoms of algebra, 4. Real-world applications, and 5. Unsolved mysteries of math. We're starting with a tangible hook and zooming all the way into the abstract math that powers our modern world.
Section 1. The language of symmetry. The blueprint. Okay, just look at this absolutely staggering number. There are roughly 43 quintillion. That's 4.33 times 10 to the 19th possible states of a standard Rubik's Cube. Think about that sheer volume of permutations. Yet every single one of them is governed by a single group of transformations. It isn't just some chaotic mess. There is a highly organized, strict mathematical boundary holding all those quintillions of states perfectly together. Now, as a quick refresher, for any mathematical system to officially join the club and be considered a group, it has to satisfy 3 foundational axioms. First up, associativity. Basically, grouping your operations doesn't change the outcome. Second, an identity element. You can think of this as a zero-turn action on our puzzle that leaves it completely unchanged. And third, the multiplicative inverse. This guarantees that every single action you take has a precise reverse move that completely undoes it. Hit those 3 marks, and boom, you have a group. And this brings us to a major divide in algebra. On the left, we have abelian groups, where the math is commutative. That just means the order of operations doesn't matter. Doing action A and then action B yields the exact same result as doing B and then A. But on the right, we have non-abelian groups. Our Rubik's Cube falls squarely into this category because it's non-commutative. The sequence of your twists fundamentally changes the final result. If you twist the right face and then the top, you get a totally different cube than if you twist the top and then the right. Order is everything. Moving on to Section 2, Hidden Structures, Subgroups, and Cosets. This brings us to a really elegant concept, Lagrange's theorem. It's this beautiful counting relation that essentially proves internal structures within a group aren't just random. If you find a hidden subgroup, let's call it H, its size must perfectly divide into the total size of the overarching finite group G. It lays down an incredibly strict architectural rule for exactly how symmetries nest within one another. But, what happens when these groups just become overwhelmingly massive? Well, By using a really clever process called quotient mechanics, we can cleanly simplify them. Step 1, we identify a normal subgroup. That's one that remains invariant when subjected to a structural test called conjugation. Step 2, we group elements into mutually disjoint sets called cosets. And finally, step 3, we essentially collapse that entire complex space down into a much simpler factor group. It's just a brilliant way to zoom out and see the broader structure without losing any of the underlying mathematical truth.
All right, section 3, atoms of algebra, simple groups.
The classification of finite simple groups is honestly one of the greatest achievements in all of mathematics. It took decades of work, but mathematicians finally proved that every single atomic group fits perfectly into one of 4 categories. We've got cyclic groups acting as prime-order building blocks, alternating groups handling even permutation structures, continuous groups of Lie type, and finally the sporadic groups. Now, there are exactly 26 of these rare, exceptional, sporadic groups that completely refuse to follow the rules of the infinite families. And among those 26 rare, sporadic exceptions is the awe-inspiring monster group. And I mean awe-inspiring. It is an atomic structure so incomprehensibly massive, its exact size is the 54-digit number you're looking at right now. That's over 8 times 10 to the 53rd power. And remember, this is a simple group. It's considered indivisible in this framework. It acts on a 196,884 dimensional space known as the Grease algebra. Just let that scale sink in for a second.
And this equation right here brilliantly illustrates exactly why the monster group is so mind-bending. This represents monstrous moonshine, which was an almost mystical discovery made by Richard Borchards. He astonishingly linked the dimensions of the monster group directly to elliptic modular functions, which normally belong to a completely different mathematical realm. See that number 196,884 in the equation? Yeah, that perfectly matches the sum of the dimensions of the first 2 irreducible representations of the monster group. It literally proves an invisible bridge exists between abstract algebra and complex analysis. Absolutely wild.
Section 4. Real-world apps. Theory meets reality. Now let's bring this down to earth. Every single time you send a secure text message or log into your bank account, cyclic groups and subgroup mechanics are acting as the invisible shields protecting your digital life. The discrete logarithm relies on prime fields to make hacking computationally intractable. Triple Des uses symmetric permutations but intentionally avoids group closure to prevent the security space from collapsing on itself. And looking ahead to the future, Shor's algorithm uses quantum Fourier transforms over cyclic groups, which could one day break these discrete logarithms in polynomial time, completely upending modern cryptography as we know it.
And if we look out into the cosmos, continuous Lie groups flawlessly dictate the actual laws of physics. The Pauli matrices act as the generators for SU2, which dictates 2-dimensional quantum spin spaces. The Gell-Mann matrices provide the explicit representations for SU3, governing quantum chromodynamics, basically the color symmetries of quarks. In fact, the entire standard model of particle physics, the very rules that dictate the strong, weak, and electromagnetic fundamental forces, is built entirely upon a single, massive gauge group constraint. It's all group theory.
Finally, Section 5. Unsolved Mysteries. The frontier of math.
Because math is never truly finished, right? Decades-old dilemmas, like Burnside's problems, continue to push the boundaries of decidability and algorithmic computation today. The foundational question asks, if a group is generated by a finite number of elements, and every single element has a finite order, is the group itself necessarily finite? The fascinating answer is actually no. Mathematicians like Golod and Shafarevich found infinite counterexamples. However, bounded variants of this very problem remain deeply mysterious to this day.
Or take the Herzog-Schonheim conjecture. It's this really elegant theory about cosets proposed way back in 1974. It essentially asserts that if a group is partitioned into a finite collection of cosets, at least 2 of the indices must be equal. What's so fascinating about this is the current state of the proof. It has been brilliantly proved for finite simple groups and for symmetric and nilpotent groups, but it remains agonizingly unproven for general groups at large, just taunting modern mathematicians.
So as we wrap up this explainer, I want to leave you with this final thought. If group theory already perfectly dictates our quantum reality, the fundamental structural laws of the universe, and the digital security guarding our most sensitive data, what other invisible architectures in our universe are out there, just waiting for a mathematician to decode them? The next time you look at a puzzle, or a secure website, or even just the night sky, remember, there is a beautiful, rigorous symmetry holding the whole shebang together.
what you shares.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.